Welcome to Engineering Studio with Dr. Mohammad Tahir. In this video, we are going to solve one design example related to compression members. So the given information is design a truss compression member using double angle built-up section with 10 mm gusset plate and snug tight connection. For dead load 110 kN, live load 140 kN, length of the member 3.4 meter and A36 steel. Before we start the design of compression member using built-up section, first we need to understand one thing. So we will read this note. So the section will be economical if it has nearly same slenderness ratio in both the direction. In this case, as we know, it is a truss compression member, so K will be equal to 1 because we assume that there are pin connection in case of truss members. So K will be equal to 1. And we don't have any bracing in any direction x or y, so L will be equal to LUX and LUY. So LX, LY and L, these will be equal. So if we talk about KLX or KXLX and KYLY, so these are same, these are equal. So if we want to design a economical section, so we need to select such a section that it has same slenderness ratio about the x and y axis. So if the slenderness ratio about both the axes is same, so in that case the strength of the member will be same about both the axes and we will have a economical section. So the section will be economical if it has nearly same slenderness ratio in both the direction. This means that Rx and Ry should be nearly same. So if KXLX and KYLY are same, so Rx as well as Ry should also be same to have the same slenderness ratio about x and y axis. So as the length of the both direction is equal, so we should have same or nearly same radius of gyration in x and y direction. So the radius of gyration are for the double section or x for the double section will be same as that for a single section. So if we talk about the radius of gyration of this built-up section, so the radius of gyration about x-axis will remain same as that of one section, because we know R is equal to I over A square root. So as we, in case of one section, we have the radius second moment of area equal to I, and when we have two sections, so it will be 2 times of I, and similarly the area will also be 2 times. So 2 will be cancelled out and we will left only with I over A square root. So Rx will remain same as that of the individual member, but Ry will not be same. So Ry will actually change because of the spacing between these two sections. So if we talk about the Ry, so Ry will be equal to Iy of the built-up section over area of the built-up section square root, and Iy of the built-up section will be equal to 2 times Iy of individual section or one section plus area of one section multiplied by the distance from the centroid of that section up to the centroid of this built-up section from here up to here. So AR square. So Iy will be different. So in case of built-up section, Iy will increase because of the gap between these two members. So when Iy will increase, so it means the Ry will change. So we can conclude that in case of built-up section, when they are made like this, face back to back, so in that case Rx will remain same but Ry will change, and it will depend on the spacing between the two angle sections. Okay, the radius of gyration Ry for the double section will be considerably higher than for a single section. So as I have told earlier that Iy will increase because of the built-up section, so the Iy or the Ry of built-up section will be considerably higher than that of the Ry of individual section. Okay, from the above fact, it is clear that to make R same in both the direction x and y, unequal leg angle are to be used with the longer leg connected together. So if we want to have Rx is equal to or nearly equal to Ry, so we need to select these individual members in such a way that their Rx is greater than Ry, sufficiently greater than Ry. So when the Rx is greater than Ry for individual members, so when we make the double angle or built up section, so in that case this Ry of the built up section will increase and we will reach to the value near to the Rx. So Ry of the built up section will be nearly same to that of Rx. So if we select our section in such a way that Rx of the individual member is considerably higher than Ry. So if we talk about the equal leg section, so in case of equal leg section, Rx and Ry both are same. Rx is equal to Ry. So if we want to increase the Rx value, so we need to select such a section which has one leg larger than the other leg. So if this leg is larger than this leg, so in that case Rx will be greater than Ry. And if we connect this leg, the longer leg of the two sections, so in that case our Rx value and Ry value will be same. Rx of the built up section as well as Ry of the built up section will be nearly same. So we can reread this statement. From the above fact, it is clear that to make R same in both the direction for built up section, unequal leg angles are to be used with the longer leg connected together. So this leg should be larger than this one. The projected leg should be relatively smaller. So if we select a section for which this connected leg is larger and this projecting leg is smaller, so in that case Rx as well as Ry will be nearly same. But if we select a section with equal legs, so in that case Rx of built up section will be less than Ry of the built up section. Okay, so from this discussion we can conclude that we need to select an unequal leg section with one leg or with the connected leg longer, with the longer connected leg, and the projecting leg should be smaller. So next is we need to calculate the design loads, or we need to calculate the factored applied load. So in case of dead and live, so we can combine by 1.2 dead and 1.6 live, so it comes out to be 356 kilonewton. To select the section, we need to calculate the required area, and for required area, A required, we need Pu over phi c FCR. And to calculate phi c FCR, we need the slenderness ratio value. So at the initial stages when we don't have the dimension of the section, so we can assume the slenderness ratio value. For built up section, we can assume it as 90. So our assumed slenderness ratio is 90. So we need to compare it with the RC value, critical slenderness ratio, which is 133 for A36 steel. So as it is less than RC, so it means we have inelastic buckling. So if there is inelastic buckling, we can use this expression to calculate the phi c FCR value. So it comes out to be 146.46 megapascal. Once we have phi c FCR value, then we can calculate the area required for the double angle or for the built up section. So Pu divided by phi c FCR, it will give us the required area, and this required area is for double angle. So for single angle it will be half of this, so we need to divide it by 2. So the area required for single angle will be 1216 millimeter square. Okay, once we have the required area, now we need to select the section based on these three criteria. Area selected should be nearly equal or larger than the area required. We should go for the minimum weight section, and B or the leg dimension, connected leg dimension should be more than B minimum. And B minimum, if only one leg is connected, so it will be 2.5 D plus 16, which comes out to be 54 when D is equal to 15 millimeter if we use 15 millimeter diameter rivets. Okay, from the table we can select the sections. So if we go into the table, so here we can make this selection, angle section L102 by 75 by 7.9 or 9.5. So both have the area more than 1200, the area required for single angle. So 1350 or 1600. So 1350 is close to this value and 1600 is a somewhat larger value. So we can select these two sections, or we can also look for some other section. For example, this one 1250, it has area close to the required area, but in this case the longer leg dimension is close to the shorter leg dimension. So we need to select such a section in which one leg is larger and the other leg is shorter or smaller, because we need the Rx value sufficiently larger than Ry for single angle. If this is so, then the Rx of built up section will be nearly equal to Ry of the built up section. So we need to select such a section in which one leg is considerably larger than the other. So we can select this value. So here we can select these two sections. So I have reported these sections over here. So here one more section is also selected by just keeping in mind this area. So area of double angle. But here the both legs are same, so we will not use this, because in that case Rx and Ry will be same for single angle, but when we use it as a built up section, then Ry will be considerably larger than Rx. So the larger value of Ry will not have any benefit. Okay, so now our selection is these two sections. Okay, once we have selected the section, then we need to check the section for global instability and local instability and the compressive strength. So first of all, we make the trial, or we check this section 102 by 76 by 9.5, and we need to check whether it is okay or it can resist the applied load without any local as well as global buckling. So the area of this section is 2 times 1600, mean 3200 millimeters square for the built up section. So if the next is to apply the checks. The first check is we need to check whether the B minimum is B is greater than B minimum. So B is, in this case, the dimension of connected leg is 102, so it is more than 54, so it is okay. So the B of the selected section is more than B minimum, so it's okay. So the next is we need to perform the checks of local instability. For that, the slenderness ratio lambda B over T, it should be less than lambda R. So here we need to see that we have one leg 102 and the other leg 176. So if we take B over T for 76, its value will be less, but B over T for this 102, its value will be larger. So we need to consider the larger value, so we will calculate B over T for larger leg, so 102 divided by 9.5. So it should be less than lambda R. And the limiting value for the lambda R can be calculated by using this table. So for angle sections, unstiffened members of angle section, so we need to use this expression to calculate the value of lambda R, and it is 12.8. So the B over T for the angle section is 10.7 and it is less than 12.8. So it means the local instability check is satisfied. Okay, next is we need to calculate the slenderness ratio. So in case of built up section, we need to consider the slenderness ratio about x-axis and y-axis for built up section, and we also need to calculate the modified slenderness ratio about the axis for which there are relative deformation between the sections. I mean, one section have compression and the other section has tension, or both have relative deformation. So when they have relative deformation, there will be shear between the members, and to resist the shear we need to provide stay plates or tie plates. So when we provide stay plates or tie plates, in that case we need to calculate the modified slenderness ratio. So if we see, in that case we need to calculate the slenderness ratio R about x-axis, we need to calculate R about y-axis, we need to calculate R modified, we also need to calculate A over R minimum for individual section to ensure that the individual section should not buckle within the tie plate. So we need to investigate these 4 slenderness ratios. So first of all, if we calculate the Rx value, so for Rx, slenderness ratio about x-axis, so it will be Kx Lx over Rx. So K is 1 in case of truss member, L is 3400 and Rx is 32. We can select this value from the table. So it is 32. So its value comes out to be 107. To calculate slenderness ratio about y-axis, we need to calculate the Ry value for built-up section. So in this case, we have the built-up section like this. So either calculate the exact value by using this expression Iy is equal to Iy of the built-up section, if I write over here. So Iy of the individual section plus area of individual section multiplied by the distance from the centroid of the section, of centroid of the built-up section up to the centroid of the individual section. So it will be actually x plus 5, because the spacing between the two members is 10, so the half of will be 5, so x plus 5. So I write it as r, so r square, ar square. So we need to multiply it with 2 because we have two identical sections. So in this way we can calculate the Iy value. So it will give us the exact value of Iy, and from the Iy we can calculate Ry. But we can also approximate the value of Ry by using this expression which is given in the LRFT manual. So here B is the total width of the section. So if we see, our section is like this. So this is 76, this is 10, and then again it is 76. So 2 times 76 plus 10, so it will give us B. So it is 162. So the expression for the slenderness ratio of built-up section is B times 0.19 plus S over 1270, and here S is the spacing between the two members. So B162 into 0.19 plus S is 10 millimeter, the spacing, divided by 1270. This spacing is actually equal to the thickness of gusset plate. So the slenderness ratio of the section about y-axis, the Ry radius of gyration about y-axis comes out to be equal to 32.06 millimeter. And if we compare it with Rx, so it is almost equal to the Rx value. So Rx of the built-up section as well as Ry of the built-up section are nearly same, and this is only possible when we select a unequal leg section. So by using this Ry value we can calculate the slenderness ratio. So 1, K is equal to 1 L 3400 divided by Ry, so it gives us the slenderness ratio. So now we have these two slenderness ratios. Next we need to calculate the slenderness ratio of individual member between the stay plates, but before that we need to decide the spacing of stay plates. So for example, we have the sections like this, angle section. So one stay plate is over here and the other stay plate is over here, and we assume that the thickness or the width of this stay plate is 75 millimeter, here 75 millimeters. So the clear spacing between these two will be equal to A. We assume it is A, and the center to center spacing between these stay plates or tie plates will be equal to A plus 75. And we have guidelines regarding this A over R value, or A slenderness ratio of the individual member between the tie plates. So we have guideline that the A over R minimum for the individual section between the tie plates, it should be less than 0.75 times R maximum out of these two. So by using that expression or that information we can calculate the value of A. So selection of stay plate spacing, so we have A over Ri or K times A over Ri. So here K will be equal to 1 in case of snug tight connections. So A over Ri should be less than equal to 0.75 larger of KLX, means slenderness ratio about x-axis and slenderness ratio about y-axis. So the larger value is 107, 0.75 times 107, so it will give us 80.25. So A over R minimum is equal to 80.25. And if we see in case of angle section, we have three axes: x-axis, y-axis, and z-axis, and correspondingly we will have rx, ry, and rz. And in case of angle section, this rz will be the minimum. So we need to select the minimum r value out of these three, and that is equal to rz, and its value is 16.4, and these we can select from the properties table. So rz is 16.4, so if we substitute this r minimum with 16.4, so we can get the value of a. So a maximum will become 80.25 times rz, means 16.4, so it will give us the clear spacing between the stay plates. So once we have the clear spacing between the stay plates, now we can decide the number of stay plates. So for example, we have one angle section and the other angle section. The total length is 3.4 meter, and if we see the center to center spacing between these tie plates, so it will be equal to a plus 75, mean 1.316 plus 0.075, or if we write in millimeters, so it will be 1316 plus 75. So it will be the center to center spacing between the stay plates. So once we have the center to center spacing between the stay plates, so we can calculate the number of spaces for this built up section. Number of spaces between the stay plates for this built up section. So for that we need to divide the overall length, which is 3400, by this factor 1316 plus 75. So it will give us a number which is comes out to be 2.45. So it means there are 2.45 spaces between the stay plates. But this number cannot be in fraction, so it should be either 2 or it should be either 3. So for example, we say that the number of spaces are 3 instead of 2.4. So if the number of spaces are 3, so it means there will be 2 stay plates. So there will be 2 stay plates in between the member, one over here and one over here. So in that case we will have 3 spaces. So now we have decided that there should be 3 spaces and 2 number of stay plates. Now we can find their distance, or the clear distance between the stay plates. So to find the clear distance between these stay plates, what we will do, we will subtract the center to center distance between the stay plates. We will subtract the thickness of the stay plate from the center to center spacing of stay plates. So the center to center spacing of stay plate will be 3400 divided by 3, because there are 3 spacing, and if I subtract 75, the width of the stay plate, so I will get the clear spacing between the stay plates, and it comes out to be 1058 millimeter. So initially what we did, we determined the a value by fulfilling this condition that a over ri should be less than 0.75 r value. So from here we get the a value, and based on that a value we have checked how many spaces will be there. So it comes out to be 2.45. so either we need to have 2 spaces or 3 spaces. So let's say there are 3 spaces, so it means there will be 2 stay plates. So if there are 2 stay plates, 3 spaces, then we can calculate the center to center distance between the stay plates. That will come 3400, or the overall length of the member divided by 3, and if I subtract the width of the stay plate, so it will give us the clear spacing between the stay plates. So once we have the clear spacing between the stay plates, after deciding the number of stay plates, so now we can calculate the actual value of a over r minimum. Okay, a over ri or a over r minimum, so a is 1058 divided by r minimum is rz, which is 16.4, so it comes out to be 64.53, and it should be less than rx and ry. Okay, and this is 64, and rx and ry are 107 and 106, so it means it's okay. So now we need to calculate the modified slenderness ratio, and we calculate the modified slenderness ratio about an axis for which there are different, or we can say for which there are relative deformation between the members or between the elements. So if we see this built up section, if we talk about x-axis, so in that case both the section on this side as well as on this side of the section will have same deformation if it bends about or buckles about the x-axis. But if this built up section buckles about the y-axis, so in that case one member will be in compression and the other member will be in tension. So in that case there will be relative deformation between the two members, two elements of the built up section. So in that case we need to calculate the modified slenderness ratio. So we will calculate the modified slenderness ratio about y-axis. So for snug tight connection, the modified slenderness ratio about y-axis will be equal to slenderness ratio Ry of the built up section plus A over R, in Ry square plus A over R square. So it will give us the modified slenderness ratio, and this modified slenderness ratio will be larger than the Ry value. So now we have Rx, Ry and Ry modified. So we need to select the largest value out of these three, and the Ry modified is largest out of these three, which is 125 millimeter, 125. The largest of kxlx over rx and modified ky ly over ry. So it is 125 and it should be less than 200. So 125 is less than 200, so it means the global instability check is satisfied. So once the global instability check is satisfied, then we need to proceed further to check for the axial capacity of the member. So to calculate the axial capacity of member under compression, we need the phi CFCR value. So based on this slenderness ratio, we will calculate phi CFCR value. We need to compare it with RC. If it is less than RC, and it is less than RC 133, so it means we need to calculate the phi CFCR value by using inelastic buckling formula. So we have discussed that formula many times. So it comes out to be 98.28 megapascal. So once we have phi CFCR, we need to multiply it with the area of the section, and it will give us the capacity of section under compression, and its capacity comes out to be 314 kilonewton, which is less than 356 kilonewton applied load. So it means it is not good. The capacity should be more than this applied load, so we need to revise the section. Okay, now we will go for a higher section with larger value of area as well as the smaller value of Ry, because if we see the capacity of the section depends on Ry value, because phi CFCR depends on Ry. As the Ry goes on increasing, so its value decreases. So we need to decrease this value to enhance this phi CFCR. Now we need to revise the section in such a way that the capacity of the section is more than this applied load. And if we see the capacity of section depends on phi CFCR, and phi CFCR is linked with this slenderness ratio. So to increase the phi CFCR value, we need to reduce this slenderness ratio. And if we want to reduce the slenderness ratio, which is critical about y-axis, we need to increase this Ry value. So we need to select such a section which has a larger value of Ry. So when the Ry will be larger, so this slenderness ratio will be reduced. And when the slenderness ratio will be reduced, phi CFCR will increase, and we will have the larger or the higher capacity of the section. Okay, the next trial section, we can select a section with the projected leg a little bit larger than the previous one. Previously we selected 102 and 76 or 75, I think, but now we need to increase the dimension of this leg to increase the Ry value. So here we have selected a section with a little larger value of this projecting leg. So for this selected section, the area is 2 times 1720, mean the area of one section is 1720, and for double angle it will be 2 times. Now we need to again perform all the checks one by one. So first B, which is the connected leg dimension 102, it should be more than B minimum, and it is okay because B minimum is 54, so 102 is more than 52, it is okay. Now we need to perform the local instability check B over T. So again, the larger leg or the longer leg is 102, so 102 divided by thickness, it is 10.7, it should be less than lambda r, which is 12.7. So 10.7 is less than 12.7, so it is okay. Now we again need to perform the global instability check. For that we need to calculate Rx, Ry A over Ri and Ry modified. So to calculate Rx, we can simply select the Rx value because Rx for a single section will be same as for the built up section. So we can calculate slenderness ratio about x-axis, which comes out to be 107. And for Ry, we can calculate the Ry, the radius of gyration about y-axis, by using this approximate formula as we did earlier, or we can calculate the exact I value, and then from this I we can calculate the Ry. So to calculate the I, exact value of I, so it will be Iy of the individual section plus area of individual section multiplied by the x centroidal distance plus the half of spacing. So it will give us Iy value. So once we have Iy, then Iy divided by area of section, it will give us Ry, radius of gyration. So once we have radius of gyration, we can calculate the Ry value. So now we have Rx as well as Ry. The next step is to decide again the spacing of the stay plates. So again, the clear spacing between the tie plates is A, and the center to center spacing will be A plus 75. And to calculate the maximum value of this A, we can again use the same expression, A over Ri should be less than 0.75 R maximum. So A over Ri 0.75, larger of Rx and Ry. So larger is 107, so it comes out to be 80.25. So Ri will be equal to Rz. Ri means the minimum radius of gyration of the individual member will be Rz 18.5 for the selected section. We can see this value from the properties table. So if we substitute this Rz in this equation, so we can get the maximum value of A, which comes out to be 1.485 meter. So for 75 millimeter long stay plates, the number of spacing between the stay plates will be the overall length of the member divided by the center to center spacing between the stay plates. So this is the spacing, clear spacing between the stay plates, and 75 is the width of stay plate. So it will give us the number of spacing. So it is 2.18. So either we can go for one stay plate, or we can go for two spacing, or we can say we have three spacing. So the batteries, the number of stay plates should be 2, but the maximum number of stay plates should be 3. So we can use 2 stay plates. So if we use 2 stay plates, so we will have 3 number of spacing. So if we use 2 stay plates, so we will have 1, 2 and 3 spacing. So the center to center distance between these spacing can be calculated, the overall length divided by number of spacing. So it will give us center to center spacing between the stay plates, and if we subtract the width of one stay plate, mean half from this end and half from this end, so it will give us the clear spacing between the stay plates, and 75 is the total width of stay plate, half from one side and half from the other side. So once we have A value, so we can calculate A over Ri, the exact value of A over Ri. So A over Ri is again the Rz value, so it comes out to be 57.19. We can calculate the modified slenderness ratio about y-axis. Why about y-axis? Because about the y-axis we will have relative deformations. So the modified slenderness ratio comes out to be 103. Okay, now we need to select the larger value about out of Rx and modified Ry. So the largest value is 107, which is equal to Ry. So corresponding to this 107 value, we need to compare it with the 200, the limiting value of slenderness ratio. So it is less than 200, so it's okay. Global instability check is satisfied. The next is to check the capacity of section. To check the capacity of section, we need to calculate the 5 CFCR value corresponding to this slenderness ratio. It comes out to be 122.63 megapascal. So multiply it with the area of section, it will give us the capacity of section, the load capacity of the section, and it is more than the applied load PU 356 Newton. So it is okay. So now all the three checks mean local instability, global instability, as well as the strength of the member or the capacity of the member are satisfied. So we can select this section as a final section because it fulfills all the three criteria for compression member.